In 1940, Britain approved a desperate weapon. It was officially the No. 74 ST grenade. Most troops called it the sticky bomb. On paper, it solved a serious problem. Infantry needed something to stop tanks. The solution was simple, almost crude. A glass sphere filled with high explosive, covered in a powerful adhesive coating. The plan was brutally straightforward. Get close and make it stick to armor. But field reports quickly raised concerns. Dust could weaken the adhesive grip. Rain sometimes caused complete failure. Mud made the surface almost useless. Cold weather stiffened the compound badly. And soldiers still had to get dangerously close, much closer than standard anti-tank doctrine preferred. In controlled tests, the sticky bomb worked. In real conditions, reliability became the real question. In early 1940, Britain faced invasion anxiety. Conventional anti-tank weapons remained in short supply. Emergency committees requested unconventional infantry solutions. In the War Office, approved rapid concept exploration. Design authority moved to the Ministry of Supply. Requirements emphasized low-cost mass manufacturability. The weapon needed minimal specialist training. Engineers proposed an adhesive anti-armor device. The concept received provisional internal support. Project designation became No. 74 ST grenade. ST indicated the term sticky within documentation. Initial sketches showed a glass sphere container. The sphere contained a high explosive filling. Outer surfaces required strong pressure-sensitive adhesive. Developers selected nitroglycerin-based explosive composition. The filling used a nitroglycerin and stabilizer mixture. The casing required controlled fragmentation avoidance. Engineers prioritized blast effect against armor plating. Early prototypes used standard industrial glass molding. Glass thickness required precise manufacturing tolerances. Excess thickness reduced adhesive surface conformity. Insufficient thickness caused premature handling fractures. Protective external casing enclosed the adhesive surface. This casing prevented accidental sticking during transport. The outer shell used two thin metal hemispheres. Operators removed the shell immediately before deployment. Designers incorporated a timed fuse mechanism. The fuse delay averaged approximately 5 seconds. Ignition relied on a spring-loaded striker assembly. Safety procedures required manual arming steps. Testing began under accelerated wartime conditions. Initial blast trials occurred at controlled proving grounds. Results showed adequate explosive energy output. Adhesion performance became the primary concern. Laboratory surfaces provided unrealistically clean conditions. Field simulations introduced dust contamination variables. Adhesive strength dropped under particulate exposure. Moisture further degraded bonding reliability. Rainwater significantly reduced surface tack effectiveness. Mud contamination produced frequent complete detachment. Cold weather stiffened the adhesive compound. Temperature sensitivity required additional material research. Chemists modified the adhesive composition repeatedly. Each revision produced inconsistent bonding outcomes. Production urgency limited extended material refinement. The War Office maintained pressure for rapid delivery. Procurement officers prioritized quantity over optimization. The mass production planning began despite unresolved concerns. Glass suppliers received emergency manufacturing contracts. Adhesive formulation required specialized chemical facilities. Explosive filling operations followed strict safety protocols. Factories implemented compartmentalized blast mitigation layouts. Workers received limited hazard training initially. Handling accidents occurred during early filling runs. Safety reports recommended improved protective equipment. Output targets remained unchanged despite incidents. Packaging required careful separation of components. Transport crates included internal shock cushioning. Moisture ingress during shipping caused early failures. Storage depots reported adhesive degradation over time. Shelf life estimates required downward revision. Field units received the first operational batches. Training manuals described close-range deployment procedures. Infantry were instructed to approach armored vehicles. Recommended throwing distance remained dangerously short. Operational doctrine assumed limited enemy mobility. This assumption proved frequently inaccurate. Troops reported difficulty removing protective casings. Cold conditions stiffened the metal shell halves. Gloves reduced manual dexterity during arming. Dropped units occasionally shattered before use. Breakage produced hazardous explosive leakage incidents. Command reviews noted rising safety concerns. Adhesion tests against painted armor showed variability. Dust-covered armor defeated the bonding layer. Oil residues further reduced attachment success. Field improvisations attempted surface cleaning before throws. Such procedures increased operator exposure time. Several training accidents prompted procedural revisions. The fuse delay remained fixed despite feedback. Requests for longer delay intervals were evaluated. Engineering teams rejected major fuse redesigns. Production lines lacked flexibility for modification. Procurement schedules overrode ergonomic improvements. Frontline reports grew increasingly critical. Users described the weapon as unreliable. Commanders questioned tactical practicality. Despite concerns, manufacturing continued at scale. Stockpiles expanded across Home Guard units. The Home Guard received priority distribution. Regular Army formations received smaller allocations. Urban defense planning incorporated the grenade extensively. Rural deployment showed limited enthusiasm. Mechanical trials examined glass sphere durability. Impact resistance remained below desired thresholds. Protective handling procedures became more restrictive. Operators required careful transport discipline. Instruction leaflets expanded with warning language. Explosive yield remained technically sufficient. Penetration relied on blast proximity to armor. Standoff detonation reduced effectiveness sharply. Successful adhesion remained mission-critical. Trials against moving targets produced poor results. Relative motion frequently dislodged the grenade. Vibration from engine operation reduced bonding strength. Rain-soaked exercises showed near-total failure rates. Chemical teams proposed alternative adhesive compounds. Supply shortages limited material experimentation. Budget authorities restricted further chemical procurement. The design entered full emergency service regardless. Distribution peaked during invasion scare months. Operational usage remained relatively rare. Reports from training environments dominated feedback. Safety officers documented handling injuries. Broken glass caused laceration incidents. Explosive seepage created additional hazards. Storage instructions grew increasingly complex. Inspection routines were added at depot level. Quality control revealed batch inconsistency problems. Adhesive viscosity varied between production lots. Temperature during manufacture affected final performance. Factories lacked uniform environmental control. Moisture contamination occurred during adhesive application. Rejection rates rose in several facilities. Management implemented tighter inspection checkpoints. Throughput slowed but remained politically protected. War Office memoranda acknowledged operational doubts. However, cancellation risked supply embarrassment. Officials maintained public confidence internally. Alternative anti-tank solutions entered parallel development. Improved rifles and launchers showed better promise. Comparative trials exposed the grenade's limitations. Nevertheless, existing inventory required distribution. Training films demonstrated correct deployment technique. Footage avoided showing adhesion failures. Internal reviews noted optimistic presentation bias. Troops increasingly preferred other available weapons. Field commanders quietly deprioritized the grenade. Home Guard units retained larger stock reserves. Periodic inspections removed degraded adhesive units. Chemical aging remained a persistent issue. Heat exposure accelerated adhesive breakdown. Cold storage slightly improved longevity. Logistics chains struggled with climate control. Transport by rail introduced vibration stresses. Some shipments arrived partially compromised. Depot workers filed repeated condition reports. Engineering teams considered container redesign. Time constraints prevented major structural changes. Operational doctrine shifted towards supplementary use. The grenade became a contingency measure. Frontline reliance steadily decreased. Manufacturing eventually slowed under revised priorities. Existing stockpiles remained in storage. Post-crisis analysis documented systemic shortcomings. Reports emphasized environmental sensitivity problems. Adhesive chemistry required conditions rarely available. Glass fragility complicated safe deployment procedures. Close-range requirement increased operator vulnerability. Procurement reviews labeled the design expedient. Historians later categorized the device as improvised. Technical files recorded the emergency origin clearly. The number 74 remained a notable wartime experiment. Its development reflected severe material shortages. Engineering compromises were evident throughout documentation. Operational doctrine adjusted around its limitations. Eventually, superior anti-tank weapons replaced it. Remaining units were gradually withdrawn from service. Surviving examples entered controlled storage facilities. Archival records preserved full production data. The project remains studied within ordnance history. It demonstrates pressures of invasion preparedness. The sticky bomb illustrates emergency engineering trade-offs.